Hello, everyone. I'm Zhaomo. Today, I will be presenting our paper, Dashboard Elimination Still Considered Harmful. Concerns over memory disclosure vulnerabilities in C and C++ programs have led developers to explicitly scrap sensitive data from memory. A typical scenario might look like this. So you allocate a buffer in heap, and after the last use of this buffer, you call memset to scrap the sensitive data so that even if there's a memory disclosure vulnerability, that could not leak the sensitive data. In this case, it's a password. However, in reality, this example most likely won't work because compilers perform an optimization called dead store elimination, or DSE for short, which removes stores that have no effect on the program result. Developers have been aware of this phenomenon and have devised various ways to circumvent it, which led to a proliferation of secure memset implementations of varying quality. So in this paper, our goal is to understand the current state of dead store elimination problem and developers' attempts to circumvent it. So I will start first with a survey of existing techniques. Among more than half a dozen techniques we found, several are flawed, and none are both universally available and effective. Then I will talk about our case studies and to help you to understand the use of memory scrubbing in reality. Last but not the least, I will present our solutions to solve this problem. First, let's look at the existing techniques. So due to the time limit, I will not cover all the techniques we found in the wild. To look at the rest of the techniques, please refer to our paper. For each technique, I will first describe how it is intended to work and its availability on different platforms and its effectiveness. We rate the effectiveness of a technique on a 3-level scale. We consider a technique is effective if it's always guaranteed to work. And we consider a technique is effective in practice if it works on GCC, Clone, and Microsoft Visual Studio, but it's not guaranteed to work in principle. And a technique is flawed if it fails in at least one configuration. The easiest way to scrap sensitive data is to use a platform-supplied scrubbing function that guarantees the desired behavior. On Windows, there's secure zero memory. On OpenBSD and NetBSD, there's explicit B0, which also has been adopted by glibc recently this year. These functions are effective, but they are only available on certain platforms or in certain versions of a specific library. So one may wonder that why doesn't the C language provide a universal way for developers to scrap sensitive data? Actually, the latest C standard, C11, does have a function for this. So in the latest version of C standard, this is the function called memset_as. Memset_as is considered as a secure version of memset. It does some runtime checking of its parameters. Also, calls to this function cannot be optimized out by a standard conforming compiler. While this seems like the ideal solution for developers to scrap sensitive data, the implementation of this function has been slow. Actually, as far as we know, there's no C library that provides this function in a standard conforming fashion. There may be several reasons for this. First, this function is a part of the Annex K, which is an optional annex. This means a standard C library is not required to provide this function. Also, C11 treats all the functions in this annex as a unit. That is, if a C library wants to implement memset_as, in a standard conforming fashion, it has to implement all of the functions defined in this annex, which seems to be a lot of work. Also, there are library developers arguing that some functions in this annex are poorly designed. In the end, there's still no universal way for developers to scrub sensitive data, and the burden of fighting the compiler is still on developers' shoulder. In a thread that requests a glibc implementation of memset S, a glibc developer suggested the requester to use no built-in memset option instead. So here's the reasoning behind this technique. So to improve performance, compilers normally replace the calls to memset with its built-in equivalent. And some developers believe that compilers only know the semantics of the built-in memset, not the C library memset. However, this thinking is flawed because the semantics of the C library memset is decided by the C standard. And there's nothing prevents the compiler from knowing the semantics of this function. What's more, we found that this technique is also not guaranteed to work in practice. Starting from glibc 2.3.4, when the optimization level is higher than O0, which is the normal case, and the macro fortified source is greater than 0, the fortified version of memset is enabled. Note that this version of memset is enabled regardless of whether no built-in memset is used or not. Here is the definition of this fortified version of memset. So first, this is an inline function. And what it does is first doing some parameter checking. And then it calls a built-in memset that does additional bounce checking. However, this built-in memset is subject to GCC's death store elimination. So this means even when you disable built-in memset by using no built-in memset option, a built-in memset can still be used, and that memset will still be subject to death store elimination. So in summary, this technique is flawed, not only in theory, but also in practice. The next group of techniques I will talk about attempt to hide the semantics of the scrubbing operation from the compiler. The high-level thinking goes, if the compiler cannot recognize that an operation is clearing memory, it will not remove it. The simplest way to hide the semantics from the compiler is to implement the scrubbing operation in a separate compilation unit. For example, when the platform is not Windows and the compiler is not a GNU compiler, Kerberos uses a scrubbing function defined in zep.c. This scrubbing function is only used outside of this compilation unit. Here, developers expect this to work because they believe that defining the scrubbing function in a separate compilation unit will prevent the compiler from inlining and understanding the scrubbing function at call sites. However, this is not guaranteed to work when link time optimization is enabled. What link time optimization does is essentially merging all the compilation units into one at the intermediate representation level, and then performing regular optimizations, including death store elimination on the single compilation unit. So when link time optimization is enabled, such a scrubbing function can be inlined. And when it is inlined, the call to memset will be subject to DSE. So in summary, although this technique is universally available, it is flawed Another very popular way to hide the semantics of a scribing operation is to call the scribing operation via a volatile function pointer. So OpenSSL cleanse is one of the implementations based on this idea. So here, on line 2, memset_func is defined as a volatile function pointer point to memset. And OpenSSL cleanse uses this function pointer to clear memory. So developers expect this to work because they believe the call to memset via a volatile function pointer is a volatile access, which the compiler cannot optimize out. However, this behavior is not guaranteed by the C standard. Let's look at how C standard defines a volatile object. So here, this is the paragraph from the C standard on this topic. In summary, the standard says that a standard compliant compiler cannot optimize out any volatile access. However, a standard compliant compiler is free to decide what constitutes a volatile access. So let's go back to OpenSSL cleanse. So the volatile function pointer is used on line 5, which actually consists of 2 steps. First, reading the volatile function pointer. Second, calling the function pointed by this function pointer. So the first step is widely considered as the first step, reading a volatile function pointer, or in general, reading a volatile object is widely considered as a volatile access. But calling a function pointed by a volatile function pointer may not be considered by a standard compliant compiler. And in theory, such a compiler can inline each call to OpenSSL cleanse as the code snippet here. So what this code snippet does is first checking if the pointer points to memset. If that's the case, it will just call memset directly. And in this way, the call to memset on line 3 will be subject to DSC again. So in summary, although this technique is very popular and is effective in practice, it is not guaranteed always to work. Okay, so the next group of techniques all attempt to force the compiler to include the scribing operation without hiding its nature. So a very popular way to force the compiler to perform a store is using a pointer to volatile char. So here is an example from cryptography coding standard. So on line 2 and 3, a void pointer is first cast to a pointer to volatile char, P, and then P is used to scribe memory. Developers expect this to work because they believe memory writes via pointer P, which has a type of pointer to volatile char, are volatile accesses, which the compiler cannot optimize out. However, again, this is not guaranteed by the standard because it boils down to what constitutes a volatile access. It's accessing a non-volatile object via a pointer to volatile char, a volatile access. It seems to be entirely reasonable for a compiler not to consider such an access a volatile access. And for that compiler, this technique would not work. So again, in summary, this technique although this technique is effective in practice, it's not always guaranteed to work. Another way to force memory writes is to use a memory barrier. GCC supports a memory barrier expressed using inline assembly statement. So here's an example. The Clauber argument memory indicates to the compiler that the inline assembly statement may read or write memory that is not specified in the input or output arguments. And mem0 explicit from Linux is based on this technique. So here, on line 6, there's a memory barrier. This memory barrier tells the compiler that the inline assembly statement may read the memory pointed by S, forcing the compiler to keep the call to memset on line 5. We have verified that this technique is effective, but it only works with compilers that support memory barriers. To show you how difficult it is to create a reliable and portable scribing function, let's look at this inline assembly statement. According to GCC's documentation, this is a perfectly fine memory barrier. And in fact, we have verified that this does work with GCC, since Clan also supports memory barrier with the same syntax. And in general, Clan mimics the behavior of GCC. So one would expect that this would also work with Clan. However, it doesn't. That is, memory writes before this barrier may be optimized out by LLVM's elimination. So a more reliable and portable memory barrier is shown at the bottom. This is also the one that is used in mem0 explicit from Linux. So the difference here is that this memory barrier, the pointer to the memory to be cleared is made explicit to this memory barrier. Okay, so next I will talk about our case studies. So to understand the use of memory scribing in practice, we examined 11 open source libraries and applications. For each project, we set out to determine whether a memory scribing function is available, effective, and used consistently. We noticed that many projects rely on a collection of techniques and use the first one available on the platform in an order of preference specified by the developer. In that case, we consider an implementation effective only if all the techniques it depends on are effective. Our methodology consists of two parts. First, we manually analyze each project to determine whether a memory scribing function is available and whether it is effective. And then we instrumented the Clan 3.9 compiler to report instances of destroy elimination, where a write is eliminated because the memory location is not used afterwards. For each project, we used this compiler to determine whether the memory scribing function was effective and used consistently. So here is our results. First, we found two projects, NSS and OpenVPN, didn't have a memory scribing function. All they have is a macro that expands to a plain call, a direct call to memset. An additional two projects didn't have a reliable memory scribing function. Libsodium's memory scribing function is not reliable when link time optimization is enabled. Kerbal's memory scribing function is not reliable because it used an invalid memory barrier, as is shown here. Besides, we found four other projects didn't use their reliable scribing function consistently. And in some cases, the unscribed data is actually sensitive. For example, this is a case from Libgcrypt. And in this case, a direct call to memset is used to scrub sensitive data, even though Libgcrypt does have a reliable scribing function. Our case studies led us to two observations. First, there's no single accepted scribing function. Each project mixes its own cocktail using existing scribing techniques, some of which are flawed or unreliable. Second, even when a project has a reliable scribing function, developers may forget to use it. our observations from our case studies inspired us to create two solutions, one library-based solution and one compiler-based solution. Our library-based solution is a scribing function called secure mem0. This function combines most of the effective and effective in practice scribing techniques we found in a simple implementation. Developers are allowed to specify an order of preference in which an implementation will be chosen by defining macros. Although we cannot guarantee that this implementation will work with every standard compliant compiler, we believe this is the best of breed scribing function. Besides, we have released our implementation into the public domain, and we plan to keep it updated as compilers evolve. Our compiler-based solution is a scribing-aware death-through elimination pass. So our observation is that a scribing operation satisfies the following conditions. First, the stored value is a constant. The number of bytes stored is also a constant. And the store is subject to elimination because the variable to be written is about to be out of scope without being read. So our DSE pass preserves all that stores that satisfies these conditions. Although our death store elimination pass cannot help when the developer doesn't know the need to scrub sensitive data, our pass can help when the developer forgets to use the reliable scrubbing function, which we believe is not uncommon, as is shown by our case studies. In conclusion, we surveyed the existing techniques to circumvent death store elimination problem. Our case studies show that real-world programs still have unscrubbed sensitive data due to incorrect implementation of scrubbing function, as well as from developers simply forgetting to use the secure scrubbing function. To solve the problem, we developed a scrubbing-aware DSE pass that preserves all the scrubbing operations and secure mem0, a best-of-breed scrubbing function. Thanks for your attention, and I'd like to take any questions.
Very nice work. This is Ding Hao from Penn State. I'm wondering that if you add a new global variable and then after the memory set, you just read the value, read the buffer into the global, would that solve the problem? So
you're saying that basically you are suggesting a way to implement a scrubbing function?
Right.
So basically you read and write a global variable to use that as the source use that to fill the buffer.
Kind of like a memory berry. So after you set it to 0 for the buffer, and you read again from the buffer into a global to prevent the compiler from optimize the out.
Yeah, so actually OpenSSL used to use that to scrub sensitive data. But the problem with that is that it's very slow, and you can refer to our paper to see the performance difference. I believe that one is the slowest one among all the scrubbing techniques.
What will happen if you just read like one integer, a few bytes from the buffer into the global? Not the whole buffer. Would that still prevent the compiler from optimizing the mem set that way?
So when do you? So basically you read-write that global variable to fill the buffer, right?
No. So you still do mem set to 0 for the buffer, and then after that, read from the buffer into
but after that, but I think compiler is smart enough because after the mem set, compiler knows the value of the buffer is 0, so it may not. So it may just.
But it's used by the global variable.
Yeah, but you only use, basically you only set, basically what you do is setting the global variable to 0, right?
Right.
So so in that case, basically there are two different things. One is scrubbing the buffer. The other one is setting the global variable to 0. So I believe compiler will still set the global variable to 0, but the first step, the setting the buffer to 0, will be optimized out. Is that clear?
Okay. You mean eventually the mem set will still be optimized away?
Pardon me?
You mean the mem set?
Yeah, mem set will be optimized out.
Okay, thanks.
Hi, I'm Ed Schwartz from Carnegie Mellon. I was wondering if you had any thoughts on maybe whether the semantics of the volatile flag should be changed, because it seems like the way that they're defined right now in the standard, they're not very useful.
Yeah, but I think this is true for a lot of things in the standard, right? I think one reason standard defines it this way is that it gives the flexibility for the implementation on different platforms. So if you want to change this, you may also want to change many other things in the standard or have a new standard, essentially.
Okay, thank you.
If no more questions, let's end this session. Let's thank all the speakers one more time.